Thank you very much. So yes, the title of the talk is Data Dreams. And the subject I'm going to explore here is generative AI, which I'm sure everyone here has heard lots about. But in particular, how I think the kind of core technologies underlying generative AI will be applied to new fields, to science, to business, to healthcare, to finance, to all sorts of areas where large amounts of data have been collected. Okay, so hopefully I can play that. Oh. No? Okay, my video doesn't seem to be playing here, but you've probably all seen it anyway. Maybe if I do that. Well, not to worry. I think we've all seen a lot of, seen and read a lot about generative AI over the last few years. It's really exploded. And so, just to give you a quick summary of some of the highlights, some of the things that are out there, I think ChatGPT is probably the single best known sort of, instantiation application out there. It's a chatbot. You talk to it, it replies. It's a generative model in the sense that it is generating text. So like, the data, the sort of space that it's working in is the space of natural language and text. And it's what we call conditional generation, right? Conditioned on the prompt you give it, it writes something back. And that's how most of these generative models work at the moment. So for example, Midjourney and other image generation programs, you typically type in what you want the image to look like, and it generates one, or actually it'll generate several different variants of an image that sort of match your prompt. We have Sora doing the same thing with videos. We have apps like Speechify, which it's also a generative model in a sense. What it's doing is it's taking a piece of text and reading it to you, often in the voice of, for example, a famous actor or a musician or something like that, a recognizable voice. And at first glance, these things kind of seem like magic, like the computer just sort of conjures up this new piece of information, this new piece of video or imagery or whatever it is out of nothing. But, maybe before I kind of dive into, what's going on with these models and what we can do with them, I think one thing that's important to realize is that, like a lot of new technology, it's maybe not as new as it seems at first. So just to kind of go back in history a little bit, I would say that the first thing that you could kind of consider a generative model in the modern sense would be an n-gram language model, and this actually dates all the way back to the sort of early 20th century, the work of Markov. I think he was looking at Pushkin's poetry and modeling the probabilities of whether the next character would be a vowel or a consonant. And this sentence here, this generated sentence, "You are uniformly charming," this is generated by what's called a trigram language model. So this is a language model that looks at 3 words basically and predicts what the next word will be. And it does that just by keeping track of how often sequences of 3 words appear in the data. And so in this case, it's trained on Jane Austen novels, and so you can kind of see that in the text that it generates. It generates something that doesn't really make any sense, but it has a kind of Jane Austen-ish feel. And so it's kind of important to realize that at this level, generative models that created something that sort of at surface value looks like real data, they're actually an old thing. I would say that a big step forward initially came maybe back in 1990 when Ellman started looking at a very simple form of recurrent neural network that could be used to predict the next character in a piece of text. And that was the point when language models kind of moved beyond n-grams and started being something that looks more like the kind of the modern form. And then I would say that the kind of core technologies of the current generative models mostly came out in the 2010s. I had a paper back in 2013 which did online handwriting generation. So given a piece of text, it would basically write it like natural human handwriting. And this was kind of, obviously compared to the generative models we have now, it doesn't seem so amazing in that it's only handwriting, but I think it was one of the first times a very generic predictive algorithm, this was just a long short-term memory recurrent neural network that was just doing next step prediction. It was one of the first times that an algorithm like that was used to generate data that really looked real. And it was also promptable in something similar to the modern sense. So by giving it a little bit of handwriting in a particular style, and then asking it to continue writing, whatever your prompt was, it would retain the style. So it already had this kind of ability to keep the context around when it was generating new data. Another big landmark in generative models, although they've kind of fallen out of favor now, were what's called generative adversarial networks, or GANs for short. These images here, these kind of blurry faces, came from the original paper, but in the few years following that paper, there was a kind of an explosion of interest. And I think GANs were maybe the first type of generative model that could really generate very realistic-looking photographs. So people's faces that looked kind of more or less indistinguishable from real faces. And just a little bit after that, actually, another model that's become very important lately was published. These were diffusion models published back in 2015. Once again, when they were published, they went largely unnoticed. And it wasn't until 2019, 2020, around about then, that there was basically this sudden explosion of interest in diffusion models when people kind of solved a bunch of the technical problems that went with them. And use them to start generating, and they're now sort of like the cutting edge for image generation. That's what most of these, Midjourney and similar models, that's mostly what they're using under the hood. And diffusion is kind of interesting in that it has this kind of iterative process where it takes noise and gradually denoises it and turns it into an image, which is actually similar to the Bayesian flow networks that I'll talk about later in this talk. And then I guess, the other maybe key point to mention here is the point when large language models really started, and this was with the landmark paper from 2017 called Attention is All You Need. And this was when this sort of particular neural network architecture called a transformer really took off. And the quote here is actually this was from GPT-2, which came out a couple of years later, which now seems like old hat, but to me at the time, it was I remember when I first read this prompt and I saw that it was generating a story that more or less made sense about unicorns in the Andes, and that was one of the points where it was really clear that, the time had come for this technology. But okay, to sort of take one step back and maybe demystify these things a little bit, it's important to realize that, all they are actually is probability distributions. They're parametric probability distributions fit to data. So, even if you're not, from a kind of mathematical background, you're probably familiar with the idea of, just fitting a curve to data. So, for example, we have here height data for men and women that's been gathered from a sample, and the curves that have been fitted are normal distributions, Gaussians, because we know that, this data, when a large enough sample is collected, becomes approximately Gaussian. And so that is, in some sense, a generative model, right? That's a probabilistic model that's been fit to data, only it doesn't seem to us that it generates anything. All it would generate is the height of a random man or a random woman, which doesn't seem that interesting. And the key point is the place where the magic appears, the place where you start generating, faces that look like faces and videos that look like videos, is when you start being able to model not one variable, not two variables, but really millions of variables. So if you think of, all the pixels in an image, even a single HD image, you might have, millions or tens of millions of pixels. Once you get into video, it's going to go even higher than that. Similarly for audio, or if you think of the number of words in a novel or something like that. And not only do you have millions and millions of variables, they're all interrelated in really complex ways. The thing that's made these generative models powerful is the ability to capture these interrelations. Okay, so just to kind of, underscore those points, when I think about this issue of many variables, I often come back to this short story by Borges from 1941, The Library of Babel, at least in the English translation. And he sort of envisioned this library where all possible books existed. Right? The library is total, and its shelves register all the possible combinations of the 20-odd orthographical symbols. And as he said, that's not an infinite number, but it is a ridiculously large number. So I tried to do a sort of back-of-the-envelope calculation on, how many books that would mean, and I came up with this, enormous number, as opposed to, the maybe 10 to the 80 particles in the universe. So obviously, this library can't be built in reality, and that means that in the same way, we can't build a statistical model of books in the way that we would build a statistical model of height data. We can't enumerate all the possibilities and say, how likely is this one, how likely is that one? So there's something there's a difference in quality here that comes from modeling so many things at once. And another kind of touchstone there, I guess I often think of, Michelangelo saying that every block of stone has a statue inside it, and the task of the sculptor is to discover it. So for him, if you think about, you could imagine a sort of 3D sculpture model that worked in voxels or something like that, and you feed it into a 3D printer, it would have the task of kind of finding the sculpture in the block of marble. And what's crazy is that if you think about the number of possible shapes you could make out of that block of marble, almost all of them would mean nothing. Almost none of them would correspond to, a beautiful classical statue. And so it was kind of like Michelangelo's genius that he could see that one point, if we think of it as a set or as a space, he could see that one point in this astronomically large set that captured, the thing that he was trying to create. And in some sense, that's what you have to do with the generative model. You have to pick out a vanishingly small subset of the possible combinations of these variables that gives you something meaningful, something that actually corresponds to the data. And yeah, as I said, the other issue is it's not just that there's lots of variables, it's they're all really closely interrelated. And you can see this, this is kind of innately obvious to us. We know that, all the words in a text influence one another and have a kind of shared meaning. But, you can also see this when you analyze the behavior of these neural networks. So you can look at things, for example, with transformers, you can trace the use of attention internally by the network to get a sense of what it is that the network is attending to, what pieces of information is it bringing together in order to make a particular decision, and you find that it's immensely complicated. I think in this, what this chart here on the left shows is, while it was attempting to kind of resolve which word the word "its" refers to, this anaphora resolution problem of linguistics, and obviously it's partly dividing its attention between the two things that it could refer to in that sentence. But if you go further back into the map of attention used by the network, you find that it's drawing links between every word and every other to varying degrees of intensity. And you see this all over. You see this in this other example we have here. There's a diffusion model that is kind of, I think it's jointly modeling text and image. And you can see that depending on what the text is, I'm not sure if that's legible to everyone, it says, a furry bear watches a bird. And depending on where it is in the sentence, it's basically attending to different parts of the image. So the word bear, of course, it's focused on the bear. The word bird, it's focused on the bird. Other words, it's focused elsewhere. Everything there, the words, the pixels, everything is influencing everything else. So yeah, those are the basic challenges to do the generative models have to face. And I think the really, very simple key point to make here is that it succeeds, right? So this is an image from, these images are from a paper from 2019. This was done by some of my DeepMind colleagues while I worked there. And I think this was one of the points where I really accepted, okay, these models really do work. These two faces look like real people to the extent that your mind is kind of automatically invents a sort of backstory for them, a history, right? They're real people who've had lives that pre-existed this image. Except, of course, they're not. They were just generated by the machine. But what's really exciting here is to realize that, okay, that's great. That's great that it can create realistic pictures of faces. But if we think about what that means for all of the other data that exists in the world, it seems safe to assume that we can start modeling far more complex sets of data with far more complex interdependencies than we ever have before. Oh yes, and a brief point here, and I think this is probably not going to work because the videos don't seem to be playing. No, okay, maybe I'll just describe what's going on in this scene because I find it quite interesting. So people often talk about hallucinations. They say, you know, one of the problems with large language models and other generative models is that they make up stuff that's not real. And that's actually, you know, it's kind of fundamental, and in some ways I would say that hallucinations are a good thing. So, you know, no model is going to be perfect. We're used to the idea that the weather forecast might be wrong, or that any sort of statistical model of behavior will sometimes capture things and sometimes not. But when a normal statistical model is wrong, that's just something we accept. We don't think of that as it's not a hallucination that the weather forecast said it would rain today and it didn't. It becomes hallucinatory when the model is wrong in an interesting way. So when you see a video of a glass dropping and when it hits the table, instead of exploding or shattering, it splashes like water. I think this actually happened with one of the Sora videos. Or when, you know, it generates an image of a horse that looks very realistic, except that the horse has an extra leg. And what to me is interesting about this is they're kind of like, they're semantic errors, they're high-level errors that, you know, basically tell you that the model has actually done a very good job of learning the low-level structure in the data, and now the mistakes it's making are something that are much more interesting to us. There are more mistakes in the underlying world model that generates this data. But anyway, this is sort of an aside, but I would say hallucinations will always be there. The models will never be perfect. We're asking them to generate things that, you know, we think, basically we're asking it to say, generate something plausible. And, you know, sometimes it'll get it wrong. It'll generate things that we look at and we say, okay, that's not plausible. But also that's where you learn. These are very valuable in the sense of that's where you learn what's going wrong with the model. That's how you diagnose it. Okay, so just to get it back to a little bit more of a mathematical footing, and don't worry, this isn't going to be a very mathematical talk, but I think one crucial thing to get across here is this idea of factorization and joint probabilities. So I've said we can think of the data as just a joint model of many variables. If you thought like all of the pixels in the image, those are all just x1, x2, up to x1 million. They're all just separate variables. And we've learned this joint distribution over all of them. Then the chain rule for probabilities, just basic math, says, well, we can factorize it any way we want. We can say the probability of x and y together equals the probability of x times the probability of y given x, or the probability of y times x given y. And basically what that does when you start looking at that in terms of data is it allows us to query the data. It starts allowing us to ask what-if questions. So in this simple case shown here in the figure, we've got a 2D Gaussian. And if we just say x is along one axis, y is along another, then we can say, okay, if we're going to set x equal to 3, then what's the probability of y? And that will itself be a normal distribution, and vice versa. If y is 10, what's the probability of x? Again, that doesn't look very interesting when you're just looking in two variables, but we start thinking about that applied to large complex data sets, it becomes very powerful. So if we look at this from, and it's an important point to make that, you know, from the perspective of learning, machine learning has tended to be siloed into different tasks. What is it that you want this model to do? What are you training it to do? But often different tasks just correspond to different factorizations of the same data. So for example, I used to work on speech recognition. Speech, basically, you know, the sort of the sum total of the data that you're looking at is the audio data and the text. And so for speech recognition, you want to know what's the text given the audio. For text to speech, so for when you're generating your Siri is, or rather probably ChatGPT is talking to you, then you're doing text to speech. So given some text and perhaps also given some parameters describing the speech, the voice type, you know, the tone and so forth, generate the text. If you were just to model Y on its own, then you're doing language modeling. You're doing what GPT-X does. If you're just generating speech on its own, well, that's something there's less interest in that as a task, but I guess you'd have something that just babbled on, just spoke about anything. But all of these things were kind of historically have been treated as in fact, even currently, are generally treated as completely separate tasks. But it's important to realize that if you've learned the joint distribution of those two variables and you can then factorize it afterwards, then you get all of these tasks in one go, basically. Similarly, for images and captions, we had, okay, this slide is now maybe a little bit out of date. This is going back to 2021, but we were looking at that point. Clip and DALL-E were the latest two OpenAI models. DALL-E was saying generate an image given a caption. Clip was saying generate a caption given an image. They're kind of two sides of the same coin. They're modeling the same joint distribution just from different angles. And just by kind of playing around with the order, you could basically go from one of these things to another. And what's important is that there is a joint distribution, that somehow the texts and the images live in the same space because they describe the same world, right? We're using words to describe an image. There's a picture that captures an image. There's something shared there. And then you can even go a little further with that and say, okay, what about not just saying, condition one modality on another, but what about what's called in-painting or a partial factorization of X? So if you say, take an image and remove part of it, and then tell me what the missing part is. If you've got a joint model over the whole image and you can factorize it any way you want, then this is, again, just another factorization. It says, what's the probability of X without the mask given the mask? And here's an example of the kind of thing you get. You take this picture of a woman's face, you remove the part that kind of tells you what her expression is, and then you generate from it with a powerful model that captures the joint distribution, and you'll get all sorts of different expressions and slightly different faces that are all consistent with the face that is already visible. Okay, so so far so good, but this is all about kind of text and audio and video and all of these kind of familiar things. And I should say, it's not an accident that those are the things that we've generated first, right? Those are the things that look cool. Those are the things where you create a demo and the whole world can look at it and say, wow, that's amazing. I can understand immediately that that's generating an image because I'm human and I understand images and I can read text. But of course, there's an awful lot more data than that in the world. And I kind of feel that, the next step, and another thing to kind of stress here is that the algorithms themselves, the neural networks themselves, the architectures, the training methods, all of those things, they're actually very generic. There's very little in them that is in any way specialized to text, to videos, to audio. It's actually quite surprising how similar all of these different, the models for all of these different data types are. So, just to take as a kind of example, in Nascence, my previous company, we looked a lot at industrial data. And of course, in industrial settings, in factories and so forth, people are gathering tons of data. They've got sensors everywhere. And we kind of looked at a few test cases and thought, okay, there seems like there's four main types of data. There's what we call static data, which is the stuff that's kind of fixed before operation, that tells you, okay, what's the type of process? What's the location of the factory? Maybe what's the date that a particular process is being run at? What's the ID of the machine and so forth? Then there was operation data, the things that the operator controlled during the process. There was the sensor data, the stuff that was measured as the process went on, which could be, and often these were things that aren't directly controlled. It might be something like temperature or machine state, or it could be a measurement of, whether or not there's a fault somewhere in the machine. And then finally, you have a bunch of data that's along the lines of outcome data, the stuff that you use to assess the performance, the failure rate, the tolerance, of course, the cost overall. But you can see, once again, we've got these different classes of data. So I've kind of called these A, B, C, and D just for simplicity. If you kind of change the order that you're modeling them, meaning like you condition on some things and you model others, you change this factorization, you get all these different tasks. So if you're predicting the outcome given the operation and the sensor readings, then I'd say you're getting something like performance prediction, right? How well is this thing going to perform given a particular set of operations, and that's only one hop away from control, because if you can predict the outcome given the operation, then you can start learning to optimize the operation. And needless to say, that's something that every factory wants. If you add in A, the static data, you got the same thing basically, but it's now conditioned on instances. And where that might become useful is, for example, let's say you've got many different but similar machines, and you want to have a single model to fit to all of them. As long as you can tell the model, okay, this is machine A, this is machine B, this is machine C, then you can kind of share this learning among all of those different models and use the information about which particular machine it is, rather, to kind of switch between them. Then there's lots of other tasks you can get. So sensor anomaly detection would be something like just build a model of sensor data, a marginal model, a model that kind of like averages out over all of the other things, and just tell me when the sensors have told me something they shouldn't have told me, something that's an outlier. But basically, what I would always say, what's become my catchphrase basically, whenever someone comes to me with some data and says, okay, I've got this data, I've got a particular task in mind, what should I do? My answer is always the same, it's model everything. Take all of your data and build this joint distribution. So in this case, model the static data, the operation data, the sensor data, the outcome data, all in one go. And then once you've got that, then you just need to be able to factorize it at use time. You need to be able to choose, which things you're going to set and which things you're going to predict. But by modeling everything, it's not only that it gives you more flexibility, it's essentially all of these models work better with more data. So the more you model jointly, the more you give the system to chew on. And this is really, let's say, when it comes to modeling to large language models, that's maybe less of an issue because there's so much data out there. When it comes to modeling data that you've gathered in a particular scientific process or in a particular factory or something like that, it's much more of an issue. Data is always limited. And so it's really crucial, if you want to make a good generative model, to get every scrap of signal you can out of the data you've got. So you should really try to get the model to learn everything it can about the data. Another way to think about this is the joint model is the world model, right? It's like a sort of general education for the model. And once it has that, it can be easily specialized to particular tasks. Okay, so this maybe just kind of reiterates what I've already said. You want this kind of one model to rule them all. You learn the joint distribution first, and then you fix any part of the variables and predict any other. And okay, these are mostly speculative examples, but you can imagine if you had a joint model over meteorology, over all of the instrument readings you could gather together, then just by saying, okay, at inference time, I'm going to say, fix the readings that I've got today or over a certain window of the past for particular instruments, and then give me a probability for rain. Then you're doing you're doing weather forecasting, even though you haven't trained the model specifically as a forecaster. Protein structure, given protein sequence, of course, that's exactly what AlphaFold does, and obviously it's very interesting for my current work at BioNTech with InstaDeep. Okay, probability of market crash, given world news. I realize I'm the least qualified person in this room to talk about that, but if you could hypothetically build a joint model that looked at market behavior alongside world news, then in principle you could say, okay, what's going to happen, what's likely to happen to the market if war breaks out or there's another pandemic or something like that. Okay, so that's sort of an overview of the let's say the motivation here, which is to say, okay, we know that generative models work, right? I really think there's just enough evidence there. I mean, even if what you see doesn't convince you, you have, ChatGPT passing exams, you have all sorts of, quantitative measures that show that these things really are, they're very powerful. And I should say, to me, the issue is not, are they really intelligent? Are they really intelligent? Is this AI? The question is, are they modeling the data? Have they learned the structure and the dependencies that are present in the data? And for the rest of the talk, I'm going to talk about a specific class of generative model that I introduced with some colleagues last year called Bayesian flow networks. And this little animation here kind of relates to the way that the flow of information that happens inside these networks. Okay, so maybe first thing I should say is it's a very mathematical paper. It's 50 pages long. It has more than 200 equations. Even people in the field complain that it's difficult to read. So for that reason, I'm really not going to go into any of the mathematical details here. This is going to be a very, very high-level overview. But as a sort of first, first approximation, let's say, to what they do, they're a model designed to model joint distributions over many variables, like other generative models. They are closest of the current existing generative models. They are closest to diffusion models. Both sort of sets of model have this kind of coarse to fine-like behavior, where they start off, they're repeatedly, so maybe I should say that, a kind of competing approach, the one that's used by, for example, ChatGPT, is what's called autoregression, where you predict one variable at a time. You predict the next word or word piece. Once you've predicted that, you predict the one afterwards, and so forth, which works particularly well for text. But for most data, you don't really want to choose an order like that. You rather want to say, okay, make a prediction about all of the data at once and then refine it. And so it's easy to see for images, for example. You want a kind of like, it's almost like an artist's sketch that then gets refined to a detailed painting. You want to start off with a kind of imprecise view that gives you the big picture and then gradually refine that. And so the way these models work, essentially, they try to predict all the variables at once. Initially, those predictions are very imprecise, and then as they follow this kind of prediction schedule, they end up being more and more precise. And it's this iterative procedure, which often takes thousands of steps. It can be quite computationally intensive. And this is what allows the models to resolve all of these complex interrelations between the different parts of the data, the way everything influences everything else. But really, the key difference between Bayesian flow networks, BFNs for short, and diffusion networks is that the diffusion networks work directly on noisy versions of the data, whereas Bayesian flow networks operate on distributions over the data. The kind of underlying idea was to say, okay, let's say I've got all of these different variables and I start off knowing nothing about them. So I have what we call an uninformed prior, a prior distribution. And then I gradually gather information about the variables. I can update those distributions. And the nice thing about sort of classical Bayesian statistics is as long as you stay in the simple realm of one variable at a time, as long as you treat them all independently, these updates can be done perfectly, analytically in closed form. There's a sort of known way of saying, if I at first believed that, let's say there's 10 possible things that could have happened, and I at first believed they were all likely, and now I've received some piece of information that tells me, well, actually, there's maybe a slightly higher probability that the second element of the set happened and a slightly lower probability that the sixth one happens. And we receive a bunch of pieces of information like that. There's a kind of mathematically optimal way to integrate all that information and end up with a final belief. So this is what it's kind of using under the hood. But it has to be said that in practice, at least for continuous data, so we think of an image as being a bunch of continuous variables where the variables capture the intensity of, say, the RGB channels in each pixel. Actually, that data is discretized typically because, for example, there's only 256 allowed values, but that's a sort of technical point. The equations for Bayesian flow and diffusion in that setting end up being very similar, with the one slight difference that a Bayesian flow network starts off with this kind of uniform prior, where a diffusion model starts off with complete noise. So it's actually a little hard to see in this figure, but you can see in both sets of images here, there's something where you have an image, a clear image emerging from noise, or emerging from, say, emerging from noise, essentially. But the difference is, on the very far left with the Bayesian flow network, there's kind of, it's uniform rather than noisy. So to try and make that a little bit more concrete, the path that a particle follows, a single variable follows, during this Bayesian flow process is given by this figure on the top left. It starts off at a fixed point, which is the point all the way over to the left of the image. Then it kind of spreads out. The probability of where it will go next spreads out, and then it kind of comes to a focus again at another point. In contrast to diffusion, where it just starts off maximally noisy and gradually becomes less noisy. And this is, it's kind of a subtle difference, but it seems to be significant for some types of data. So, for example, people have successfully applied BFNs to generating molecules and to modeling the coordinates of individual atoms and molecules. And so, for example, the kind of noise that you get in diffusion models is not problematic for images because you can add white noise to pixels without sort of massively changing the structure of the image. But if you start perturbing atom positions within a molecule, it has much more sort of radical effects on the molecule's properties. So sometimes having less noise is important. And I think BFNs in some sense have the minimal amount of noise possible for this type of process. But where they get a bit more interesting is when you look at discrete data, and I apologize, it's always hard to put text like this on slides so that it's actually visible, but the key difference is that because diffusion operates on data and Bayesian flow networks operate on distributions over data, the distributions, the beliefs about the data are always continuous. So in this case, if you've got 26 characters or whatever it is, you have a set of 26 numbers, all between 0 and 1, that tell you how probable you think each character is at each point. Whereas the diffusion model is constrained to actually work with discrete data. So if you look at the figure on the top right, you can see it starts off, while it's generating data, it starts off with this kind of gobbledygook of just random letters, and then gradually, with certain probability, those letters get flipped at each step, and gradually you end up with something that looks like actual text. It says, even first 1710 of India, and I have to apologize that the text doesn't really look very natural in this data because they've taken all the dates and turned them into numbers and then a whole bunch of other things. So it certainly doesn't look like the kind of thing you're used to seeing from large language models. It's really more of just like a prototype to study the behavior. And this is in contrast with the BFN, where I've used this type of diagram here where the size of the letters in each of these rows corresponds to the degree of belief that the network has that letter is present at that point in the sequence. And it starts off, all the letters are kind of almost the same size. It has this kind of uniform belief. It could be anything at any point. Gradually, it becomes more and more confident about, specific words until it gets right to the bottom when it's pretty much sure of, that it's this lyric stew and another from 1349, whatever. Okay, that all sounds like a kind of obscure technical point. What it really means from a practical point of view is that everything is continuous with Bayesian flow networks in a way that it's not with diffusion and also wouldn't be with autoregressive networks. This is useful because if it's continuous, it means you can differentiate it, you can pass a gradient through it, and that's kind of like the engine of deep learning, of these generative models. They call it backpropagation, which is really just the chain rule applied to gradients, but that is a powerful tool that allows you to kind of manipulate these processes in ways that you can't when they are discrete. And so the kind of overall picture is, okay, making everything continuous, even when there's discrete data, does a couple of things. One of them is it generally makes learning faster, and I think this is basically because there aren't these sharp changes in the data anymore. Everything's smooth, there's less variance, it's more neural network friendly. It also makes sampling better because you have gradient information that you can use when you're generating from the model, and that's something I'm exploring right now. And because we can also, so we've got discrete data, we've got continuous data, but we can also adapt Bayesian float networks to other data types. So this is kind of built into them because they're based around this this kind of Bayesian statistics principle. It's quite easy to kind of modify the type of the variable and rederive the Bayesian equation. So I already did, in the paper we already presented discretized data, so things like counts. You know, if you've got an integer count, if one of your data types says, you know, how many, you're recording how many times a particular action happened during a particular process, or how many people were present at a particular, you know, venue or something like that. You don't want to treat that as a real number. It's an integer, and you can, unlike in diffusion models where you typically just treat that as a real number and then discretize at the end, with BFNs, discretization is sort of a first-class citizen. You can build it into the model. Recently, people have also extended it to angular data. So, for example, if you've got a, you know, a number that measures a rotation, it goes from 0 to 2 pi, and then of course it goes back to 0 again. And you can build that into the model, so that it's not just treated as a continuous number with a weird jump at either side. So, like, overall, the big picture is that what we're really pushing with BFNs is that they're great for heterogeneous data that contains a mix of different types: labels, tables, charts, time series, images, graphs, everything. And the key point there is, like, that's the data you're actually going to find in real-world settings. You're not going to get these nice, clean, curated machine learning data sets where you have tons of text all cut to the same, you know, length, or images all rescaled to the same size. You're going to get a mess of different things. And what we really want to do is model all of those with a single loss function. So we can build this joint distribution over everything, regardless of whether that's a chart, a time series, an image, whatever it is. And then once we've got that joint model, we can manipulate it afterwards so that we can predict any one part of the data from any other. And yeah, that's pretty much the end of the talk. You know, I think just to summarize, we've seen how powerful generative AI is, in the sense that we've seen it create these astonishing, you know, images and videos and things like that, but we haven't yet seen, I think, what it can do when we apply it to all of the other types of data we've got in the world. And when you think of the implications of that, of, you know, medical diagnosis, for example, or you know, industrial control, or, you know, scientific, you know, all sorts of scientific fields, it's really huge. And yeah, another point that I, you know, really want to make is, most of the time when you're asking, what do I want to do with this model, you're really saying, how do I want to factorize the distribution of this model? Most questions you want to ask about the data that you've got come down to the form of, well, if I set this part of the data to that, if I turned this switch on and I ran this process for this amount of time, then what would happen to the rest of the data? And so, you know, this approach, I think, can really be revolutionary in that, you know, if you look at what, for example, empirical scientists do at the moment, they gather a large, you know, body of data in the field, and then they start asking a few, you know, fitting models to ask very specific questions. Can they classify, you know, a particular, you know, the presence or absence of a particular type of bird in some field recordings or something like that? But this could be done with a much more powerful model that really, you know, looked at all of the data they gathered together, and they could then ask so many more questions of afterwards. And I think that Bayesian flow networks are sort of really well positioned to make this step from kind of individual modalities that we see at the moment for generative models to a kind of a more heterogeneous, real-world type approach for science and medicine and elsewhere. So thank you very much.